Today, we're embarking on a journey to explore a technology as old as civilization itself. We're diving deep into the world of ancient cooling methods, techniques that have sustained communities for millennia. Forget your modern air conditioners and energy-guzzling refrigerators for a moment. We're going back to basics, back to the earth, to uncover the secrets of a simple yet ingenious invention. The humble clay pot, often referred to as a matka in many parts of the world. This unassuming vessel, crafted from the earth itself, holds a surprising power. The claim, an unglazed clay pot seemingly defying the laws of thermodynamics, can keep water refreshingly cool, even on the hottest, most scorching days. Imagine that, a natural, sustainable way to beat the heat using nothing but the earth and the elements. No electricity, no complex machinery, no moving parts, just pure, unadulterated physics at work. It's a testament to the power of understanding and harnessing natural processes. We're going to put this ancient air conditioner to the test. We'll delve into the science behind it, replicating the conditions and meticulously measuring the results. We'll analyze the data, scrutinize the evidence, and see if it's simply a myth, a placebo effect perhaps, or if there's genuine, measurable science backing up this age-old practice. The process itself is remarkably simple, deceptively so. You simply fill a porous clay vessel with water, ensuring the clay is unglazed to allow for its unique properties to take effect, and then you let nature do the rest of the work. It sounds almost too good to be true, doesn't it? But why does this seemingly magical process work so effectively, while plastic or metal containers simply fail to provide the same cooling effect? What is it about the clay that makes all the difference? That's precisely what we're here to find out. We're going to unravel the mystery, dissect the science, and understand the fundamental principles at play. We'll build our own clay pot cooler, experiencing the process firsthand. We'll rigorously test its cooling capabilities, comparing it against other methods and meticulously recording the data. And finally, we'll break down the science behind this timeless cooler, exploring the properties of clay and the principles of thermodynamics that make it all possible. Is the refreshing coolness we experience simply a trick of the mind, a psychological effect that convinces us the water is colder than it actually is? Or is there genuine thermodynamics at play, a real and measurable transfer of heat that results in a tangible cooling effect? We'll compare different clay pot designs, experiment with various environmental conditions, and get hands-on with a piece of history, connecting with the ingenuity of those who came before us. This is about more than just obtaining cool water on a hot day. It's about understanding the brilliance and resourcefulness of our ancestors, their deep connection to the natural world, and their ability to solve problems with simple, elegant solutions. So, let's peel back the layers of this ancient mystery, examining the clay itself, its structure, and its unique properties. Let's see what makes this seemingly simple clay pot cooler tick, uncovering the secrets that have kept communities cool for generations. We'll use scientific data, rigorous experimentation, and a healthy dose of curiosity to guide us on this fascinating exploration. So, without further ado, let's get started and unlock the secrets of the humble clay pot cooler. Our experiment starts right here, at the very source of the river. This pristine location offers us the perfect starting point to explore the ancient method of evaporative cooling using a simple clay pot. We're not just collecting water, we're embarking on a journey to understand a natural phenomenon. The river itself is a vital component, providing us with a cool, flowing source of water, essential for our experiment. The gentle current and the natural surroundings create an ideal environment for observing the cooling properties of our clay pot. We're using an unglazed clay pot, a time-tested design that has been used for centuries to keep water cool. This particular pot is made of terracotta, a type of earthenware clay known for its porous nature and ability to facilitate evaporation. Its porous surface is key. These tiny pores act like miniature pathways, allowing water to seep through the clay and evaporate into the surrounding air. This evaporation process is what ultimately cools the water inside the pot. As I fill it with the cool river water, I'm mindful of the ancient technique we're employing. The act of filling the pot is more than just a practical step, it's a connection to the past, a nod to the ingenuity of our ancestors. Almost immediately the pot darkens, a visual indication of the clay beginning to absorb the water. This darkening is a sign that the porous structure is working as intended, drawing water to the surface. The clay is soaking up water and priming itself for cooling. This initial absorption is crucial because it creates the necessary moisture gradient for evaporation to occur effectively. The more saturated the pot, the more efficient the cooling process will be. This isn't just about gathering water, it's about understanding the science behind a natural cooling system. We're harnessing the power of evaporation, a process that has been used for centuries to keep things cool without the need for electricity. It's about setting the stage for science, for observing the principles of thermodynamics in action. We're creating a miniature ecosystem where water, clay, and air interact to produce a cooling effect. The pot absorbs moisture, drawing water through its intricate network of pores. This process is driven by capillary action, the same force that allows plants to draw water from the soil, becoming heavy and damp, a tangible sign of the water it now holds. The weight of the water-laden clay is a reminder of the energy required for evaporation, the energy that will ultimately cool the water inside. Exactly what we want. A fully saturated pot ensures maximum surface area for evaporation, leading to the most effective cooling. This initial saturation is crucial for the cooling process, acting as a primer for the evaporative action that will follow. Without this initial soaking, the pot wouldn't be able to effectively draw water to the surface and facilitate cooling. I place a simple clay lid on top, a rudimentary cover crafted from the same porous material as the pot itself, not to seal, but to keep out debris, preventing leaves, insects, or other contaminants from falling into the water. The lid, also porous, allows for continued evaporation, ensuring that the cooling process isn't hindered, won't interfere with evaporation, allowing the water to escape and cool the contents of the pot. The porous nature of the lid complements the pot's design, creating a unified system for evaporative cooling. With our pot filled to the brim and the lid securely in place, we have a complete water vessel, ready to perform its cooling magic. We're ready for the next step, finding the perfect location to maximize the pot's cooling potential. Finding the perfect spot, a place where the pot can breathe and the evaporation process can thrive. The journey from river to testing ground, though short, is a crucial part of the process. Is short but important, allowing the pot to acclimate to its surroundings and begin the cooling process. The pot feels alive, a testament to the natural processes at work. Cool and damp in my hands, a refreshing sensation that hints at the cooling power within. This act connects us to centuries of tradition, to a time when people relied on natural methods to keep cool and comfortable. It's a reminder of the ingenuity and resourcefulness of our ancestors. We have our vessel and water, the essential ingredients for our experiment. Now, let's find the ideal place to let science work, a spot where the pot can demonstrate its remarkable cooling abilities. The stage is set, the actors are in place, and the natural world is ready to witness the magic of evaporative cooling. Time for the clay pot's performance. Time to witness the ancient art of cooling in action. Placement is everything. You can't just leave the pot in the sun and expect miracles. We need shade and airflow protection from direct sunlight, plus a gentle breeze. Our first spot under a dense tree on cool, shaded earth. The ground acts as a heat sink, and the breeze powers our cooling system. For our second setup, we use banana leaves to create a humid, shaded microclimate. The leaves block sunlight and regulate evaporation. Two test locations, one relying on airflow and ground contact, the other on natural insulation. Both shield the pot from the sun and encourage evaporation. The wrong spot would doom the experiment. By choosing carefully, we give the clay pot its best shot. Now, we wait. Time for the showdown. Clay pot versus metal cup. Both filled with river water at the same temperature, both left in the same shade. The metal cup is our control. I measure the air, 32 degrees Celsius. The metal cup's water, 31.5 degrees Celsius. Almost the same as the air. Metal conducts heat, so the water warms up. Now the clay pot thermometer in, and the numbers drop. 30, 28, 26, finally 24 degrees Celsius. That's a 7.5 degrees Celsius difference. Genuinely cool water. The clay pot isn't just keeping up, it's actively cooling. This isn't a myth or a trick, it's real, measurable science. The only difference? The vessel. The clay pot is doing something special. We've got the data. Now let's break down the science. How does it work? The answer is evaporation. Water seeps through the clay's pores to the surface. When it reaches the air, it evaporates, turning from liquid to vapor. This change requires energy, which is pulled from the water inside the pot. As water evaporates, it takes heat with it cooling what's left behind. The pot sweats, just like our bodies do to cool down. Airflow helps carry away vapor, speeding up the process. As long as there's water and a breeze, the cooling continues. It's simple, brilliant physics in action. Let's dig deeper. For water to evaporate, molecules need energy, the latent heat of vaporization. The clay pot's porous structure lets water reach the surface and escape as vapor. Each escaping molecule takes heat with it, lowering the temperature inside. Glazed pots, metal or plastic don't work. They're non-porous, so no evaporation. The unglazed clay is the hero, actively participating in the cooling. It's not just a container, it's a cooling engine. The cool, damp surface is proof of heat being pulled out. The pot doesn't just block heat, it pumps it out. This is hands-on thermodynamics, perfected over millennia, all thanks to evaporation. That's the secret. The real magic? The pores in the clay. Firing the pot leaves behind a network of microscopic tunnels. These pores let water seep out slowly enough for evaporation, not waste. The size and distribution of pores are critical. Too big, water leaks. Too small, no cooling. Generations of potters perfected this balance. The porous structure also increases surface area for evaporation. Every pore is a launch pad for cooling. The right clay firing and craftsmanship make all the difference. These invisible pores are the unsung heroes of the clay pot's cooling power. This isn't just history, it's a practical lesson from the past, a testament to human ingenuity. These ancient techniques passed down through generations offer solutions that are surprisingly relevant today. It's accessible science. The principles behind these methods are rooted in basic physics and material science, making it a fascinating exploration for anyone curious about how the world works. Anyone can try this at home. No specialized equipment or advanced knowledge is required. It's a hands-on experiment that brings scientific concepts to life in your own kitchen. First, get an unglazed clay pot. The more porous, the better. This is key to the evaporative cooling process. The unglazed surface allows water to seep through and evaporate. You'll also need a control vessel, something like a glass bowl or plastic container. This will serve as a baseline for comparison, allowing you to clearly see the cooling effect of the clay pot. And of course, a thermometer. A simple digital thermometer will do the trick, allowing you to accurately measure the temperature inside both the clay pot and the control vessel. Feel the difference in temperature between the two, or measure it with the thermometer for concrete proof. You'll notice the clay pot feels significantly cooler to the touch. Want to go further and create a more effective cooling system? Then build a Zeer pot, a simple yet ingenious form of refrigeration. This involves placing a smaller clay pot inside a larger one, creating a double-walled structure. Fill the space between the two pots with wet sand. The sand acts as a reservoir of water, constantly supplying moisture for evaporation. Finally, cover the entire setup with a damp cloth on top. This helps to further regulate the evaporation process and keep the sand moist. The sand's evaporation draws heat away from the inner pot, effectively cooling its contents. This creates a simple, electricity-free fridge, perfect for storing fruits, vegetables, and other perishable items. This technology is truly life-changing, especially in regions where electricity is scarce or unreliable. It offers a sustainable and affordable solution for food preservation. It significantly reduces food spoilage, extending the shelf life of produce and minimizing waste. And it empowers communities by providing a means to store food safely and independently. It's appropriate technology, meaning it's well-suited to the needs and resources of the people who use it. It's simple to construct, affordable to maintain, and remarkably effective at preserving food. Don't be afraid to experiment with different setups to find what works best for your climate and needs. And explore different types of clay and sand to optimize the cooling effect. The world is your lab, so get creative and see what you can discover. Science doesn't always need a fancy lab filled with expensive equipment. Sometimes the best discoveries are made with simple tools and readily available materials. All it takes is curiosity, a willingness to experiment, and a bit of earth. And of course water, the essential element that drives the evaporative cooling process. So try it yourself, build your own natural refrigerator, and connect with a timeless invention that has sustained communities for centuries. Who knows? By exploring these ancient techniques, you might just invent something new, a modern adaptation that addresses the challenges of today. The verdict: the clay pot cooler is confirmed science. Our tests showed a real, measurable temperature drop thanks to evaporative cooling. The clay pot is a passive, sophisticated cooling machine perfected over centuries. It's science hidden in plain sight, accessible, democratic, and elegant. Filling a pot and placing it in the shade reveals a dance of thermodynamics and material science. Our ancestors were brilliant engineers even without modern terminology. The clay pot invites us to explore, ask questions, and discover. It's a hands-on lesson in heat transfer, memorable and practical. In a high-tech world, the clay pot's simplicity is beautiful and effective. It works, and always will, as long as physics holds true. This ancient wisdom, absolutely, unequivocally confirmed.